Sorry, Haley. No, I didn't. I just wanted to check it out and then move on, because nobody is here. All right, let's get started. So I want to start at the back of the packet. I think most of you guys do. Guys, I would highly encourage you not to write stuff down, but just watch. It is being recorded to YouTube. Let's start with the last page, number 12. Because we're starting at the back page, they're harder than the ones that are earlier on, like this one. So it's going to seem strange at first, but honestly, if you know your crap, these aren't that bad. I set the bar low. Your job is to make sure you don't trip over it, okay? Here we go. G is the circumcenter. If G is on the triangle and G is a circumcenter, what kind of triangle must this be? Nope. A right triangle, right? Right triangles have the circumcenter on the hypotenuse, right? And not only are they on the hypotenuse, but it's on the midpoint of the hypotenuse. So that's a midpoint, right? Now, if you remember, G is called the circumcenter because why? Circumscribed circle, right? Circumscribed circle, right? Something like that. So that means that anywhere from G to the outside of the circle will be a what? Radius. So this would be a radius, right? And this would be a radius, which makes sense because they're both 10, right? All radii will be the same for the circle. But isn't also this a radius? It is, so Z will be 10. Because you know your crap, and you know that Z has to be it, right? Yeah, from here to here. Anywhere to here on the circle will be a radius, right?
Why wouldn't it go straight down?
What do you mean?
Well, it's going like
In this case, it doesn't. It's just how it be sometimes.
Wouldn't that make it longer?
Okay. Nope. It'll be the same. Anywhere from G to the circle will be the same because it's a circle, right? Does that make sense? All right. All right. What kind of lines make the circumcenter? What kind of lines form it? Nope. Special lines in a triangle.
I forgot the name.
Orthogonals, perpendicular bisectors, angle bisectors, medians, what? Which one?
Perpendicular bisector.
Perpendicular bisectors. So if these are perpendicular and they make G, right, then they must also be perpendicular bisectors, which means this and this is the same, so that's 6. And these two are the same because it's a bisector as well. We know that because G is a circumcenter. Doesn't work for anything. You can't just be like, oh, they look the same, right?
Okay,
The reason this works is because this is a perpendicular bisector.
How do you determine perpendicular?
So G is a circumcenter, and the lines that make the circumcenter from a triangle are always the perpendicular bisectors of that triangle. So if this is perpendicular, then it must also be a perpendicular bisector because G is the circumcenter. So that means it also bisects.
Where do you get 6 from? Come back. 7. Oh, 6 together. I thought you drew it.
Nope. So if we have right triangles, we should be looking for a couple things. One, it's really easy to get right triangles to be similar, gentlemen. And two, if we have right triangles, we should be able to get Pythag. No one heard that.
No.
One, if we have right triangles, we could get similar triangles, right? It's pretty easy to get similar triangles. They're only one angle short. Or Pythag, right? So how would we get X? We can do Pythag because we know one leg and the hypotenuse. And we're going to use that to figure out the other leg. We know this is the hypotenuse because it's across from the 90, right? So the hypotenuse is 10. So 10 is C, right? So that's C squared. And then we have our two legs. It doesn't matter what order you do them in. 6 squared and X squared, right? Notice just because there's a variable doesn't mean it goes here. This is the hypotenuse. The hypotenuse is always here, right? It'll happen to you. I guarantee someone tomorrow will put X here and 10 there. Don't do that. 10's the hypotenuse because it's across from the 90. So when I do math, I get 100 and 36. And when I subtract, I get X squared equals 64. So that means X equals 8.
What's 8 minus 4? 9.
Okay.
That's all you have to
So those are both 8, which means Y is what? Oh, how do I know those are 8? Let me explain. Sorry. I'm jumping ahead. X is 8, right? Do you see how this is going to be the same?
Yep.
Right? So those are both 8. So Y is going to be what? 16. And X will also be 8, right? You could have also done Pythag to figure it out, right? If you know that, if you
X 8?
X is 8 because of this right triangle,
Okay.
right? Same thing here would be a right triangle, right? Cool. You could have also said this was 6, so this has to be 6, right? Because they're right across from each other. It's a rectangle, right? So if that's 6, you could do Pythag to figure out this was 8.
That's all you had
That's
to
another
do.
way you could do it. Okay, that's it.
So earlier in this packet, does it say prove the variables?
No.
Then how do you know? All it says is G is.
We're using properties of the circumcenter. We're just applying it.
You're just trying to figure out.
We know these properties are true because we've proven them over the last 2 weeks or so, right?
Yeah.
But now we're just using them.
You're writing down all the equal lengths, and then you're basically just trying to find the least equal.
Yeah, now you wouldn't know what's equal if you didn't know how the circumcenter works, right? Circle, radii, right angles, right? There'd be no way to solve it. If you know your crap, it's easy. I love including those types of problems on quizzes. If you don't know your crap, it's impossible, right? How would you know that these are all equal? How would you know that that's a right angle, right?
So then basically
You would.
what you did is you just took the two sides. You took the tens, you put that for the solution, and you just try to find.
Yeah, all 3 of these are the same because they're radii. So that's 10.
Words are hard, math is easy.
Yeah.
Right, I'm struggling.
If you know what the circumcenter does, right, it kind of leads you to the rest of the results, doesn't it? Okay.
I got it.
Let's look at number 14. Again, it looks really complicated. It's not. What kind of center must G be? In center, because center of an inscribed circle. Anywhere from the center of this circle to the outside of the circle will be a radii, right? So that means that's a radius,
So it's all gonna be 5.
and that's a radius. What would this line be? It also a radii, right? Because it's from center to the outside of the circle. That's 5. I could draw in more, right? But like I only care about those. So in other words, the in center is always equidistant from the sides of the triangle, right? It's always the same distance from every side. Now when we measure distance, we need to make sure it's at a right angle, because you wouldn't say the distance from G to this side was this distance, right? You wouldn't do that, right? You wouldn't go at an angle. You go straight towards it. And to go straight towards something, it means to walk perpendicular towards it. So this would be 90, right? And this would be 90, because we would measure straight towards that side. Okay? Let's find y first. We have 2 right triangles here, and they share this hypotenuse. Guys, if they have the same hypotenuse and they have the same leg, by HL, aren't they congruent? They are. So if we know the leg here is root 21, what does y have to be? Root 21. Now, pretend you didn't realize they were congruent, right? Here's what you would do instead. You would say, look, I can figure out the hypotenuse here, right? How could I figure out this hypotenuse?
You can go from.
Pythag, right? Right? Those are both legs. That's the hypotenuse. So I would do 5 squared plus root 21 squared equals the hypotenuse squared, right? What's 5 squared? The only thing funnier than 24. What's root 21 squared? 21. Right? Roots and squares cancel. So that means h squared would equal whatever this sums to, which is 46. And that means h would equal root 46. So this whole length here is root 46. If you didn't realize these were the same triangle, you could plug that into Pythag and do 5 squared plus y squared equals the hypotenuse squared. Well, that's 46. This is 25. Ta-da. Right? But if you know they're congruent, it's much easier, right? Same triangle, because by hypotenuse they share, and leg that matches, right? We know these guys should match too, because they're congruent triangles. Or you could do Pythag. How do we feel about Pythag?
It's all right.
Okay. Laney? Okay. How's it go? Yeah? All right. These 2 triangles, don't they have the same hypotenuse and the same legs? So by HL, they're congruent. So if that's 12, this is 12. If you didn't know that, you could do 5 squared plus 12 squared, because those are both the legs, right? You get 169. What's the root of 169?
13.
And then you do 5 squared plus we don't know squared equals 13 squared. You do math and get 12. You do Pythag again. If you know what you're doing, it's not hard. You just need to know your properties. How many triangles do you see? 2. That's not a triangle. Gets them every time. These 2 angles are congruent. Why? Nope, not alternate. Corresponding. Yeah. Nice job. Good catch. These 2 also corresponding, right? And then they share angle A. If you want, because we know these triangles are similar, you can write the similarity statement. It might help you match stuff up. So let's start with the small triangle, ADE. What's A going to match with on the big triangle? A. What's D going to match with? And what's E going to match with? Good. So now we do CSP, and we know that AD, what's the length of AD? X. And what's AB? Not 5. What's the whole thing here? X plus 5, right? Segment addition postulate. X plus 5. Do you see that? It's whatever X is, and then you add 5. So that's kind of weird. What's DE and BC? Well, DE is 12, and BC is BC. Why? I asked the questions. What's AE? 9. A is 9. What is AC? I swear to God if you say 3.
9 plus 3.
Thank you, it's 12. It'll happen to you tomorrow. You'll be like, oh, it's 3, right? That's not part of a triangle. AC is 12. Now, did you have to do that? No. You could have just been like, look, between the blue and the purple angle is 9, and that's going to go with blue and purple on the big triangle, 12. Between blue and green, 12. Between blue and green, Y. Between green and purple, X. Between green and purple, X plus 5. Right? Same way. But if you're lost, do CSP, right? It's the thing we've been doing the whole time. We know they're similar by double angle. So now we do math. Well, I can solve this one pretty easily. What would make this easier? Simplify 3 over 12. You could do that, yeah. What else? Flipping it, right? To put Y on top. If Y is on top, it becomes much more clear of how we solve. How do I get rid of that divides by 12? Multiply. Here, you're like, I don't know what to do, right? You'd multiply by the Y, and you'd have to move a bunch of stuff over. This is much easier. Flip both sides. It's all good. So we multiply by 12. We got 12 times 12 on the top and 9 in the bottom. The reason I wrote it like this instead of 144 is because if you're clever, dividing by 9 is just the same as dividing by 3 twice, right? Right? It's the same thing. What's 12 divided by 3?
4.
What's 12 divided by 3? 4 times 4 is?
16.
144 divided by 9 is 16. You might have not known that off the top of your head, but if you think cleverly, right? Divide the 12 by 3 and 12 by 3 and you get 16. I don't know. It's up to you. Y is 16. Let's find X. So if Y is 16, I can write it like this. 12 over 16 equals X over X plus 5. Well, if that was just a 5 under here, what would you do to get the 5 over there? Multiply, right? I'm going to multiply by all of this, right? 2 terms, so I've got to wrap in parentheses. So I've got 12 times X plus 5. 12 sixteenths times X plus 5 equals X, right? Right? This guy times this guy. That's all. Multiplication happening here. If you want, you can multiply by 16 and move it over. You can. Or you can just keep it as a fraction. It's up to you. Do you want to do it as a fraction and distribute, or do you want to move the 16 over?
16
Okay, let's do that. Right? Now we distribute. Get our x's together. Terrible idea in math. Or real life, great idea in math. Divide by 4, we get x equals 15. Which makes sense, because 15 is 3/4 of 20. Mm-hmm. Nope, you could have just done mental math if you wanted to. But there's all the work. They're similar. Match up their stuff. Solve. Don't be confused by this, right? Just treat it as one idea. Make sure it's wrapped in parentheses. Okay? It isn't if you know what you're doing. And if you don't, it's impossible. If you don't know what you're doing and you feel like it's impossible, please meet with me. I can go through it a lot slower. Okay? I can help. What kind of lines must these be?
Perpendicular bisector. Orthogonal.
Orthogonals, there you go. So G must be a orthocenter. And orthocenter breaks up the triangle into similar triangles, right? Now, are these two triangles? Is this guy a triangle? No, it's because I didn't draw the last orthogonal in. If I did, I'd get similar triangles. And if you want to do that, you could do that. That would be a way to solve it. I'm not going to do that. Okay. Isn't this a right triangle? So PFAG's on the table. Do we know 2 of the 3? We do, right? We know 3, 5, and we're missing the other. Which one's the hypotenuse? 5, because it's across from the 90. So if we want to do PFAG, we'd do V squared as a leg, 3 squared as a leg, and 5 squared as the hypotenuse. And if you know your special right triangles, V is going to equal 4. Because when you subtract 9, you get 16. When you root it, you get 4. It's a 3, 4, 5 right triangle. Very common right triangle. Most right triangles have weird numbers, right? They don't come out nicely, which is why 3, 4, 5 is kind of special. Now, aren't those vertical?
Yep.
Means these two triangles are similar. We should not be surprised by that, right? Orthocenter does that. If they're similar, then we can match up their parts by CSP. Notice that if that's green and that's red and that's green and that's red, these both must be the same, right? These two angles, what's left over must be the same. If you want to do the triangle similarity thing like we did here and then get this, that's fine, that's safe. I'm going to do a shortcut. Between the red and green on this angle, or this triangle is 3, right? What's between red and green on this triangle?
7.
So 3 and 7 are going to go together. Now I'm going from small to big, so be consistent. 4 is between red and blue. What's between red and blue here? We don't know. So I'm not going to use that one. Let's just not use it, right? We can call it a letter if you want, but I don't care about it, yeah? Well, I'm going to go and find x now. I'm not proving anything. I'm just finding variables. Lengths. That's it. Okay. I'm just applying what we know. 5 is between green and blue. What's between green and blue here?
X.
So 5 goes to the small triangle and x from the big triangle. Are you following me? Right? I'm just really just doing CSP, right? Now, this problem would be easier if I flip both, right? So I'm going to do that. How do you solve a problem like Maria? Multiply by 5. No. When I multiply a fraction by 5, I multiply the top and divide by the bottom, right? What's 5 times 7?
35.
What's 35 divided by 3? 35 over 3. Doesn't simplify. Sometimes it do be like that. Sometimes it do be like that. Okay? Now, I promise I won't cram so many variables in one diagram. I just didn't want to have to draw different triangles a billion times on Microsoft Word when I was really tired. So I just did them all in the same, okay? Notice over here, we have two triangles, AGE and ACD. They share an angle, don't they? They both share angle A. So they're similar because they both have a right angle and they both have angle A. So let's match them up. I want to know what this is on the big triangle. That's Y. Now notice, if this is red and this is blue, right? If it's similar to this triangle, what angle must that be? What color?
G.
G for green. Right? It's got to be. These two go together, right? If that's red and that's blue and that's red and that's blue, these both must be the same, right? So Y is between the red and the green. Again, you could do CSP if you want, right? Write all the letters out. That's fine. I'm just going to use colors. So Y is between red and green. What's between red and green here? 3. Cool. Let's do them all. What's between blue and green? 5. That's the small triangle. I did my small triangle second, so I'm being consistent. Between blue and green in the big triangle, what's that? It'll happen to you. Z plus 4. It'll happen to you. Z is only from C to E. Is this a triangle? No. Z plus 4 is the whole thing between green and blue. See it? No need to fear that. Just treat it as one idea, right? And then lastly, what's between red and blue? 4 in the small triangle, red and blue in the big triangle. 7 plus 5, which is 12. Ah, and that's what we need, right? That tells us the relationship. What's 12 over 4? 3. So all of these are going to simplify to 3. Take it or leave it. All right, well, let's solve for Y first. How would I solve for Y?
Multiply by 3.
Yeah, so Y is going to equal what?
9.
9. You see what I'm saying? Right?
Wait, where'd you get 9?
Well, that's what Y equals, right? I'm just cutting out the middle. Schaffer, shut up.
Yeah, exactly.
So I times by 3. It's 9.
Okay.
Multiply by 3. I'm going to write this one over here because this one's a little bit harder,
Z would be 11 then.
right? We times by 5 and subtract 4, right? Times by 5, we get 15. Subtract 4, Z is 11. Nice job. Yeah.
That ain't too
What
bad.
if we didn't like see like 12 before? Can we just still do everything and then?
If you didn't see that,
Yeah.
you wouldn't be able to solve.
Well.
You'd have 2 variables but 1 equation. Does that make sense? Yep. You need all 3. That's the key. Yeah. you need to understand this part of this problem. I know you're intimidated because it's like, oh, the hypotenuse is there, and now the hypotenuse is here for the big triangle. You can do it. You can do it. Match them up. Make sure you match up correctly. Don't assume if that's the hypotenuse, this is the hypotenuse of the big guy. It's not. The hypotenuse of the big guy is this side, right? They go opposite. Check your angles. It will happen to you tomorrow. 11. G is the medicine. I told you they get easier. What do we know about medians? Because those are what those are, right? 2-to-1 ratio. So if x is the bigger part, and we always know the bigger part is from vertex to the center, right? And the smaller part is always center to the midpoint. X must be 10. What's y going to be? I'm going to write that one in. You have to have a big brain plane to get z. Just so you know, remember it's midpoint to vertex, so these are equal, right? That's what a median is. And if that's the medicenter, those must be medians, right? Big brain play to find z.
Isosceles.
These are both the same, right? So it's an isosceles triangle. Aren't these congruent by side, angle, side, right? So these triangles are all the same. That's kind of nice. This angle and this angle goes together, right? Which means these two must go together, which means these two must go together. Aren't these a linear pair? And don't they have to be equal if they're the same triangle? So if they're the same measure and they're a linear pair, what do they have to be? 90, right? They both have to be 90. Another way to think about this. If a point is equidistant from the endpoints of a segment, perpendicular bisector theorem converse says if it's equidistant to the endpoints, it's on the perpendicular bisector. Well, it's already on the bisector, right? So if G is on the perpendicular bisector, this must be the perpendicular bisector. Those are both right angles. Have to be. Have to be, because it's equidistant from the endpoints. So it must be on the perpendicular bisector.
You say Z is 20, right?
So now, if this is 5, and this is 13, and we don't know what this is a right triangle. We can do p-pag, right? So we have 5 squared, because that's a leg. Is this the leg or the hypotenuse? Leg, because it's not across from the 90. 13 is the hypotenuse. Let's call that A. 25, only thing funnier than 24. What's the square of 13?
116.
Nice. When we subtract that, we get 144, so A must be. If A is 12, and this is congruent because that's a median, right? That's a midpoint. Z is 24.
Why can't you just say that? Why can't you say that?
Can I get a repeat on like the
Z
whole thing?
equals. Why can't you
Oh,
say
I'm
that
back.
Z is equal to BC?
Completely lost my head.
I mean,
Z is what?
how come you can't say Z is equal to BC?
Z is equal to BC, BC,
Like
BC.
20.
Well, because it's not, first of all. We don't know that it's isosceles. We don't know that.
You know?
Not all triangles are isosceles. Right? This one just has different sides. All right, so what I did, are we good with X and Y?
Easy.
Not really.
Medians have a 2-to-1 ratio when they cut. So if that's 5, that's 10. If
Okay.
that's 13, that's 6.5. If that's 6.5, that's 13.
Okay.
That's it. How do you feel about Z, finding Z?
Perfect.
No,
Oh, really? Okay.
that wasn't that bad.
Yeah. You got to know that that's the perpendicular bisector. That's only true because these two are the same. I went out of my way to make sure that happened, okay? That's a tough one. If it's equidistant from the endpoints, it's on that segment's perpendicular bisector. Now, we already know it was the bisector, right? So it must be the perpendicular bisector as well. 10.
Halfway there.
If you have questions about 10, I'd like to go over it. If you just want to see it, watch the video I posted. Right? Because it takes a long time to do. It's really not that hard. If you have questions about it, I can answer questions. I'll go over the brief overview for it. Does that sound good? Okay. So first thing we do is we say, look, I'm going to make a bigger triangle around this. Right? I'm going to make the triangle that I started with, this triangle here, right? Oh, sorry. This triangle here is the triangle I started with, pretend, okay? I'm going to make the big triangle around it. And the way I'm going to do that is by making parallel lines here, right? Parallel lines here. Is this coming back to you? And parallel lines here. And we know by medial triangle theorem, you can use this to abbreviate medial triangle theorem, Triforce, medial triangle theorem. says that if we have a triangle inside another triangle and the sides are parallel, then this side is equal to these two sides. In other words, it's a 2-to-1 ratio. This is twice as big as that. Yeah? Yeah. Which means this, which means this. Okay, right. So what we're going to do is we're going to draw our parallels in. Let's do, sorry, I kind of want it to be sort of parallel. Where's my ruler? Where's the dom? I don't know. I lost the dom.
Just use the big sit down. Gotta get rid of a rock.
No.
Sit down.
No.
Right now, sit down.
It's a joke about how we should have never done that, and we're still in Iraq to this day. You know when the Iraq War started? 2003. Longest war in U.S. history. Still going on. They said it would last 3 months. And they said there were weapons of mass destruction, and there weren't. There was lots of oil, and many civilians died, way more than American soldiers. Way, way more. You want to talk about genocide. All right, so there we go. These are parallel, and by medial triangle theorem, right, we know this and this and this are all the same, and this, this, and this are all the same, and this, this, and this are all the same. That's by medial triangle theorem, okay? It's that theorem. Cool. Well, aren't these midpoints now? They don't look like it, but they are. So what I'm going to do is I'm going to draw a perpendicular bisector in. Right? Perpendicular bisect. And then by alternate interior, I get this guy, right? Well, isn't here to here an orthogonal of the triangle? I'm going to do that for all of them, and they're all going to intersect at one point, and I win. So what did I do? 1, draw your parallels. That's a parallel symbol. 2, medial triangle theorem. 3, draw your perpendicular bisectors. 4, alternate interior angles. Therefore, I win. Right? Therefore, they're concurrent. Because after I draw all of these in, this is totally 90. Like, totally 90. And look, they all intersect at one point. Look, right there is where they intersect. Amazing. No, I have had none. All right. 9. Perpendicular bisectors of triangle ABC are concurrent. That's what we're trying to prove. Are perpendicular bisectors Cevians?
No. I don't know.
What is a Cevian?
I don't know. Anything that equals, I forgot.
Nope.
I don't know.
It is vertex to opposite side. So that's a Cevian. This is vertex to opposite side. Totally works out. Is this a Cevian?
No.
No, right? Cool. So examples of Cevians would be like medians, because a median is this, right? Vertex to opposite side. It's just a specific kind of Cevian. Angle bisectors are Cevians, right? Right. Orthogonals are Cevians, right? Perpendicular bisector? You might think, yeah, right? But here's the problem,
Oh, yeah, it's got both. It can't be both. I forgot. Yep.
right? It's not always both, right? So perpendicular bisectors aren't. So we're not going to use Cevis theorem's converse to prove that this all equals 1, right? And therefore they must be concurrent. Because they're not Cevians, right? Not always. For the other ones we will, right? Except for this one. This one gets the weird, crazy triangle, right? These two we're going to use Cevis theorem and Cevis theorem's converse, right? So what we're going to use is perpendicular bisector theorem, because we're talking about perpendicular bisector theorem, or perpendicular bisectors. So I'm going to draw in 2 of them and prove the third one has to go through that same point. So let's draw in some perpendicular bisectors. Boop. That's D, E. And I'm going to draw in this perpendicular bisector. Again, not assuming it goes through B. I'm going to say they intersect at K, and I'll call it F, G. So I will say let the first line I created, DKE, right? Be the perpendicular bisector. You need those tick marks. It's not just perpendicular. It's perpendicular to what side? Nope, it's not perpendicular to there. It's CDB.
Just do CBD from B.
Nope, because B's not in the middle. I know, right? I know. And the other line I drew is FKG, right? Notice I only drew two of them. The third one I'm going to prove must go through K. FKG is perpendicular to what line? CFA or AFC? Yep. Okay. Now, I'm going to prove that if I were to draw this guy in, he would have to go through K. And here's how I'm going to do it. By perpendicular bisector theorem. Perpendicular bisector theorem says if a point is on the perpendicular bisector of a segment, right, then that point is equidistant to the endpoints. Okay? No, that's Siva's theorem's converse. That's the only one that I taught you how to do contradiction for. Okay? We're not assuming the opposite. Okay? So, isn't K on the perpendicular bisector of AC? It is, right? It's on AC's perpendicular bisector. So by perpendicular bisector theorem, it's equidistant to the endpoints. U, it's probably a K. It's a K. That's a K. That's a K. Sorry, guys. Nope. So, equidistant. Cool. That's by perpendicular bisector theorem. Isn't K also on BC's perpendicular bisector? So it must be equidistant to B and C as well. And I already have the C part, right? So, by perpendicular bisector theorem, AK is congruent to BK is congruent to CK. Those are Ks, okay? Now, notice this makes sense, because what center is that? Perpendicular bisectors make what center? Circumcenter. Those are radii, right? So, of course. Now, the converse of the perpendicular bisector theorem is this. If a point is equidistant from the endpoints of a segment, then that point must be on that segment's perpendicular bisector. So, look at the segment I don't have a perpendicular bisector on yet. Isn't K equidistant to its endpoints? Therefore, K must go through, or this line must go through K. The perpendicular bisector must go through K. Has to. It's just the converse, right? So, by perpendicular bisector theorem, converse, it's cool we use both in the same proof. We know that K is on the perpendicular bisector of what side? Of what side? AEGB. I'm just going to call it AB. Well, if K is on AB's perpendicular bisector, and we already showed it's on AC's perpendicular bisector, and it's already on BC's perpendicular bisector, they're concurrent at K, aren't they? Right? So therefore, the perpendicular bisectors of triangle ABC are concurrent. We win. We're talking about perpendicular bisectors. We're going to use their theorems, right? That's it. You feeling okay?
That was the hardest one.
I think this one's the easiest one. One of the easier ones. Let's prove perpendicular bisector theorem. How do you prove that D is equidistant to A and C if it's on the perpendicular bisector? How would you do it?
Magic midpoint of AC.
Well, wouldn't you draw the distance between AD and CD so we can talk about it, right? Let's talk about those distances and prove that they're the same. How would you do it? Shared side, right? And then by side angle side, aren't the triangles congruent?
Yep.
Well, if the triangles are congruent, then their parts are. And therefore, D is equidistant to A and C. Right? This one's a little bit harder. Nope. You would, yes. We're just running out of time. So, this one. We're proving that if it's equidistant, right, and it is, then it must be on the perpendicular bisector. This one's a little bit weirder. You have to assume that when you drop this line, it's either a 90 or a bisector of this side, meaning it's a midpoint, right? You can pick either one. I almost always pick the 90. So I'm going to say, let that be 90, right? And then I'm going to prove that these two must be the same. Because if they're the same and 90, this is a perpendicular bisector, right? It's already perpendicular. If I can prove these two are the same, then by definition, it's a perpendicular bisector, right? So how do I prove that? Well, same thing, shared side. How are these two triangles congruent? HL, hypotenuse leg. Right, can't do ass. So if they're congruent by HL, then this is true, right? By CCP. Therefore, that's a perpendicular bisector by definition. Yeah. Ooh, and get these sides? Yeah, you could. And then do angle side? Well done. Shh. No coughing. Are angle bisectors Sevians? Yeah, so we're going to use Sivas theorem's converse after we go around the triangle, okay? So I'm going to draw in some angle bisectors. Right? And I'll call that AE. So I'll say let AE exist. And it cuts two even angles, right? So CAE congruent to BAE. Now, what is triangle angle bisector theorem? That's tab theorem. That says if you have an angle bisector, then it cuts the sides of the triangle, right? The angle that you cut, those sides will be proportional to the bases you created. So that's what that means. So check it out. Didn't I cut the triangle into two sides and two bases?
Yeah.
So AC over AB will equal CE over BE by tab theorem. Triangle angle bisector, right? We're talking about angle bisectors. I'm going to use their theorem. So by tab, I know that AC over AB, the two sides, right, will equal the two bases. AC goes with EC or CE, and AB goes with this one, BE. Yeah. Okay. So tab theorem says that if you cut a triangle's angle in half, then the two sides of that angle will be proportional to the bases you created. Okay. So if I cut it in half, the two sides are proportional to the bases. Right? Thank you for asking. They're Sevian, so we're going to draw all three, not assuming they are concurrent, and then we're going to go around the triangle. Okay. So I'm going to do the same thing here. I'll call that BF. Don't worry about the point they intersect, but I'll create BF. Right. Angle ABF congruent to angle CBF, right? And then by tab theorem, doesn't this cut it into two sides, right, and two bases? So this side of the angle, AB, over BC will equal AF over CF. So AB is one side of the angle. The other side is BC. And that will equal, I did AB first, right? So that goes with AF. And I did BC second, so that goes with CF. I do that for all of them. I'm going to do another one. I'm not assuming it goes through there. That's not what I'm doing, okay? Do we know that? I'm going to prove that it will. So same dumb thing. Create CG. Create two angles. Angle ACG. And angle BCG. Well, tab says the sides of the angle go with the bases. What's the side of this green angle right here? A what? Bueller. A what? There's a C there. AC. What's the side of this green angle? BC, right? All the way through, BC. AC goes with the base AG, and BC goes with the base BG. All right, now we're ready to go around the triangle, okay? We're going to set up Sivas theorem's converse. So if I go around the triangle, starting with AG, AG over what? What's the next piece? Going around the triangle. BG. Times, next, BE and CE times CF, right, and AF. And I'm going to prove that equals 1. And if I do, I win, right? So, what is AG over BG? It's AC over BC. That's why I had to do this first. What's BE over CE? Well, it's just the flip of this, right? So if I flip it, AB over AC. Do you see what's going to happen here? CFAF. Flip it, right? You got to flip it. But it's BC over AB.
Yes.
equals 1. Right? So, by Siva's theorem converse, right? If it equals 1, then the lines must be what? Yep. Bisectors is I of triangle ABC are concurrent. They're Sevian, so you draw all three, and then use Siva's theorem's converse. Angle bisector, so you use angle bisector theorem. Yeah.
Sure.
Yes. What theorem is this? Siva's theorem's converse. How do we know it's converse? Well, we're assuming the opposite to prove it, first of all, right? In the converse, we prove by contradiction. Also, the converse is if they equal 1, then they're concurrent, right? So we assume that this is not true. Sevians, AE, BF, CD, not concurrent. Right? We're going to prove it by contradiction. Well, if they're not concurrent, like the diagram says, right, then there should be some line that is concurrent. Okay? Well, by Siva's theorem, since these are all concurrent, right, these three, then it should divide the triangle up into something that when you multiply it together gets 1, right? So by Siva's theorem, AJ over BJ times BE over CE times FC over AF should equal 1. Right? By Siva's theorem. The way this divides it up, right, because they're all concurrent, should get 1. But here's the problem. They told us earlier how this divides it up, right? Little a, little b. How that divides it up will get you 1. Well, you'll write out that that's true, right? Switch out the big letters. AD over BD equals blah, blah, blah. And what you'll get is you'll get a statement like this after you cross stuff out that are the same. And that's a contradiction. Why? Why is that a contradiction? Because how can it divide up the line like this and be the same? Right? If you cut the line at J versus cutting line at D, you're going to get two different lengths, right? So how can they be the same?
Well, aren't you using Stevie's theorem converse too?
Nope.
Or you just prove
We're proving the converse, right? So we're going to use proof by contradiction, right? That's a contradiction, this thing right here. Can't be. You can't cut the line at D and cut it at J and have it be the same length. So what we assume must be false, right? And so if what we assume was false, they must be concurrent. Proving tab theorem. Just real quick. Pick a side of the angle that's cut and extend it, or not extend it, make a parallel line to it. Like this. Extend this guy, the angle bisector, right? These are vertical, right here. These are alternate interior. So by angle, they're similar. That's an isosceles triangle. So those are both Y. AB, XY by CSP. Done. Medians. Draw them in. Vertex to midpoint. Go around the circle, setting up Sivas, right? What's AB divided by, what's AE divided by BE? AE divided by BE. What's AE divided by BE? 1, because it's the same thing, right? Times BD divided by CD. Times CF divided by AF. 1. And what's 1 times 1 times 1? So by Siva's theorem's converse, mediums are concurrent. Proving Siva's theorem. See you tomorrow. Watch that review. Best of luck. Part 1 and part 2. I do. If you have late work, I'll take it.
Can I pass?
Yes. Do you want it on this?
Yes.
Okay. What?
I was kind of sad that like it was here because I couldn't sit up here.
Oh, carpet G1 during homeroom. There you go. All right, kiddos. Maybe.
Hey, Mac.
Hi, dear. Yes, hurry.
Wipe that off, man, wipe that off. Got you in my